Okay, so yesterday we talked about heat of reaction. That is the heat that is released when released or absorbed when a reaction happens. So what do you think heat of formation is? Yeah, the heat released or absorbed when something is formed. Now, heat of formation has more emphasis in higher up chemistry classes. So AP chemistry or college chemistry, they're going to put more emphasis on this heat of formation. We're really just going to kind of look at the symbols here. So you have delta H. Remember, delta H is enthalpy, and that is heat content. So it's delta H, and the F is for formation. And then the little thing that looks like a degree sign there beside it. It's not a degree sign. It actually means that it was measured under standard conditions. But here's the kicker. The standard conditions in thermochemistry is not the same as the standard conditions for gases. The pressure's the same. It's still 1 atmosphere. But for gases, standard temperature was 0 degrees C. In thermodynamics, it is 25 degrees C. So that's room temperature, about 77 degrees Fahrenheit. It is a warm room.
I like 68. That's my favorite room temperature.
I'm a fan of 72 degrees. That's nice.
Nice.
Now, the heat of formation for elements is equal to 0 in their standard state. And I say that's because we don't have to form elements. They're already here. We just have to work with them. Substances with large negative heats of formation are more stable. That's standard. Yeah.
Thank you, Alex. Whatever you look behind my back. You're a good friend.
Now, substances with large negative heats of formation. If delta H is negative, what does that mean? Is it giving off energy or absorbing energy? Giving off energy. So if something gives off a whole lot of heat, what's remaining is much more stable because it already gave away all of its energy. Another heat of. Here is heat of combustion. So what do you think heat of combustion is? It's the heat given off when something combusts, right? And combustion is where we're burning something. So the symbol for that is delta H, or your change in heat for combustion. That's what the little C means. Now, you can't measure heat of combustion in a coffee cup calorimeter. It would be a bad move. So we have a different type of calorimeter to find our heat of combustion. And it has a really cool name, but it doesn't really live up to its name. It's a bomb calorimeter. And it's not as cool as it sounds. You basically have a little capsule that you put your sample in. It has an ignition wire. You seal the capsule, submerge it in water. You have the initial temperature of the water, then you hit the ignition switch and it combusts the material inside that capsule and the heat is transferred to the water. And you can measure the temperature change that way. And that's a bomb calorimeter as opposed to a coffee cup calorimeter. No, there's nothing cool. You don't even get to see the combustion happen. Like I said, it's a little disappointing.
They should make a see-through.
That's Okay, now we're going to calculate heats of reaction. Don't write this down because this is on the back of the specific heat worksheet that we were dealing with in class yesterday. So I want you to look at that piece of paper. Calculating heats of reaction. It's important to know what the heat of a reaction is before you actually do it, so you can avoid getting burned or frozen, those kind of things. And since we have had lots of chemists do lots of reactions, we actually have a whole lot of reactions, and we already know the heat that they're going to produce. So Hess's law is a way to use that information to figure out the heat of reaction for something that we don't already know. And so it says the overall delta H, the sum of the delta H for the individual steps. Now there are a few rules for Hess's law. The first one, we're going to manipulate these equations. So the ways that we can manipulate these reactions that are already done for us is we can write the reaction in reverse. That means you make the reactants products and the products reactants. If you do that, you also have to reverse the sign of delta H. Another way to manipulate a reaction is you can multiply or divide the entire equation by a number. And if you do that, you must also do it to the delta H values, because that's kind of the point with Hess's law. So we can do those two things as part of our manipulation for certain reactions. So here's a practice problem that we're going to work together, and then I'll have one for you guys to work. So it says calculate the delta H for the following reaction. This is going to be our goal equation. This is what we are going to try and make these guys into with our manipulations. So this is the way it works, and this is this is easier done in pencil rather than pen, because you are going to have to erase. So the way you start is you start with the first thing in your goal equation. So into. Which of these other equations has into in it? The second one. All right, then you're going to use those guiding questions, and those guiding questions are written on that piece of paper. And the first guiding question is, we see into there, is into on the same side of the arrow as it is in the goal equation? No, we need into to be a reactant, and in this equation, it is a product. So what we need to do is we need to reverse this reaction. That means we are going to write the reactants as products and the products as reactants. Now you have to rewrite the equation. Every year when I teach this, I have students who don't want to rewrite the equation and think they can do it without rewriting the equation, and they just end up confused. So don't let that be you. So I'm going to rewrite it. 2 into plus 6 H2O gives me 4 NH3 plus 3 O2. I'm going to make a column here for my delta H values. They are in kilojoules. And this one was negative 1530. But because I reversed this reaction, what do I have to do to the sign of that delta H value? Reverse it. So this is negative, so I'm going to make it positive. Everybody okay with that? No. Okay. No. Yes, it's one of the two rules. If you write a reaction reversed, you have to flip the sign. Okay. Now the next guiding question is: do I have the same coefficient as in my goal equation? I need into to have no coefficient. Okay, here I have 2 into. So what do I need to do to the whole equation so that this into does not have a coefficient? Divide by 2. Now I just kind of keep up with it over here what I have done to this equation. So I'm going to divide the whole thing by 2. So this is going to be just into. And then I'm going to erase the 6, and it's now 3. 4 divided by 2 is 2. And 3 divided by 2 is 3 divided by 2. We're just going to leave it like that. And if I do something to the reaction, I have to do something to the delta H value. So since I divided the whole equation by 2, I also have to divide the delta H by 2. And I just kind of write it down, and I'll do the calculating later. Everybody okay with that? Now, we go to the next thing in our goal equation. We dealt with N2 and got it all situated. So O2. O2 is in which equation? Both. If that happens, skip that element, or that part of the goal equation. It will work itself out. There are too many variables for you to think about. So, let's go to NO. NO, which equation has NO? The first one. And let's use those guiding questions. Is it on the correct side? Yes. So what we're going to do is we're going to write this equation down just the way it is. You want to try and line up your arrows because it's going to make things easier here in a minute. So 4NH3 plus 5O2 gives me 4NO plus 6H2O. This was negative 1170. I don't have to make it positive because I did not flip this reaction. Our next guiding question. Does the equation that we're using match in coefficient with the goal equation? I need NO to have a 2, and it has a 4. So what do we need to do to this whole equation and our delta H value in order to fix that? Divide by 2. So 4 divided by 2 is 2. 5 divided by 2 is 5 over 2. 4 divided by 2 is again 2. And 6 divided by 2 is 3. Now, you can only use each of these given equations one time and one time only. Not multiple times, only one time. I'm done. I've used each of them once, so we have to see what we can get here. I'm going to add these together. Now, this is going to be kind of like when we were working with getting rid of spectator ions. We were writing net ionic equations, and if it was the same on either side, we could cancel it out. Yes? Oh, thank you. Divide by 2. Good, because we divided the entire equation by 2. Now what we're going to do is we're going to cancel things. If they're on opposite sides but are the same thing, they're going to cancel out, and it doesn't matter which equation they belong to. So what can I cancel out? 3H2O. What else? 2 ammonia. Good. All right, there's one more thing that doesn't cancel out completely. What is it?
3 halves.
Okay, 3 halves and the 5 halves of oxygen. So when they're on opposite sides, what's going to happen is the smaller one cancels out completely, and you're going to subtract its coefficient from the coefficient you have. So 5 divided by 2 minus 3 divided by 2 is 2 divided by 2, which is 1. Everybody okay with that? All right, now if they're on the same side, you add them together. But if they're on the opposite sides, you're going to subtract the coefficients. Okay. What you're going to do is the smaller one cancels out, and you subtract the coefficient, that 3 halves, from the coefficient of the larger one. So 5 halves divided by 3 halves is 2 over 2, which is 1. Make sense? Okay. But if they're on the same side, you're going to add them together, same side of the arrow. So now I'm going to write down everything that's not crossed off. N2 plus O2 gives me 2NO. Is that my goal equation? Yes. So that means I have done it correctly. So now all I have to do is add the delta H's for these two reactions, considering the changes I've made to it, and I'll get the delta H for this new reaction. I think I ended up with 180 kilojoules. Everybody okay with that? So the next one is for you guys. So try that one. Yeah, you skip it and it end up working itself out. Dealing with oxygen. Now, to get this correct answer, what you're going to do is you're going to start with your goal equation. And so we'll start here with carbon. I see carbon in the first equation. It is on the correct side, so I'm just going to write it down. C plus O2 is me CO2, and I'm going to keep a list of my delta H values. Again, don't forget about those because that's the important part. Now, I need to get my carbons to have the same number or the same coefficient. So I need a 5. That means I need to multiply this whole equation by 5. So 5, 5, and 5 times 5. Now, you need to work with hydrogen. Hydrogen is in the second equation, and it is on the correct side. Again, I'm just going to write this down, trying to line up my arrows. All right, then H2O, negative 285.5. Now, I need my hydrogen to have the correct coefficient, so I need to multiply the whole equation by 6. It means this is 6. Oxygen now, 6 times 1/2 is 3, and then this is 6, so this needs to be times 6. The last thing in my goal equation here is C5H12. C5H12 I see here in the last equation. It is a reactant, but in my goal equation, I need it to be a product on this side of the arrow. So I need to flip this reaction. And so I'm going to write my reactants as products and my products as reactants.
Let's get 0.8. It's negative 2.
Thank you. All right, 6H2O and C5H12 plus 8O2. And since I flipped the reaction, the original one was 35, 35.6. Since I flipped the reaction, I have to flip the sign, so that's now positive. Now, I've used all my reactions, and I'm going to try and add them together. Let's see what cancels. Carbon dioxide cancels here. 6 waters cancel here. And here I have 5 oxygens and 3 oxygens. They're on the same side of the arrow, so that's 8 oxygens. On the other side of the arrow, I have 8 oxygens over here, so that will cancel with both of those. And then if I write down everything that's left, I have my goal equation. So that means I should just be able to make these modifications to my delta H values and add them together. The correct answer is 146.7 kilojoules.